This is a video walkthrough of June 2018 Paper 1 Inorganic and Physical Chemistry. Question 1 is asking you to complete a Born-Haber cycle for magnesium oxide. So you're asked to complete the missing labels. Now I would always look at where you're starting from and where you're going to. So we can see here we've got the magnesium and the oxygen are both as gaseous atoms, and we're trying to get them to the point where they're both as gaseous ions. So it's fairly obvious that we need to go through the different ionisation energies and the electron affinity. So first we're going to have the magnesium turning into magnesium plus, and it's going to lose an electron, and the oxygen stays the same. And then we're going to have it losing a second electron. So second ionisation energy. And then the oxygen is going to gain one of those electrons and do its first electron affinity. And then in the final step, it gains the second electron and becomes the O2- ion. So in question 2, we're given some data and asked to calculate the enthalpy of lattice formation. I've cut and pasted the Born-Haber cycle so that you can keep track of it whilst doing the calculation. And we can see we're being asked to do the big long arrow, which is the lattice enthalpy of formation. And if you look at the information we're given, the enthalpy of formation is the minus 602 at the bottom there, and I'm just jotting on the numbers as I go around, so I kind of assign them and work out which number corresponds to which change, because it makes it easier to add up what we've got. You'll notice for the magnesium of lattice enthalpy of formation. So if we then substitute in the numbers, so we know that the enthalpy of formation of magnesium oxide is minus 602, and we show that that's going to be equal to and put in all the values for the different sections, for the different enthalpy changes. Okay, and then if we break the sum up a little bit, so work out what the numbers on one side are and what the numbers on the other side are, makes it easier when we do the rearranging. Okay, so put the numbers all together and the delta H LEF on the other side, and we get our final value. Okay. So question 2 is about Kp. This is slightly different to ones you've seen before, because you're told the total pressure and you're told what the mole fraction of the ammonia is, and then you're only told that the nitrogen and hydrogen are put in a 1:3 mole ratio, so you've kind of got to work out from the mole fraction what the partial pressure of the ammonia is and then work backwards. So if we know that the total pressure is 150, if we times that by the mole fraction, then we can work out what the partial pressure due to the ammonia is. So that's going to be 0.8 times the 150 is 120. And if we know that the total pressure is 150, if we take away the 120, we know that the other 30 is due to the nitrogen, hydrogen, the reactants that are still left over. And we know they're in a 1:3 ratio, so I've got to fit 30 into a 1:3 ratio, or a 25% to 75%. So if I times 30 by 0.25 and 30 by 0.75, or 1/4 and 3/4, then I get the other two partial pressures. So you then ask for an expression for the equilibrium constant Kp. So as with all equilibrium constants, it is going to be the products divided by the reactants. Because it's for Kp, it's important here that we write pp and use, or p, and use curly brackets rather than square brackets, because square brackets are only used for concentration. So we put the ammonia squared because you make 2 lots of ammonia. Nitrogen is just to the 1, and hydrogen is cubed because there are 3 moles of hydrogen in the equation. So another straightforward question. You're given values of the partial pressures and you're asked to calculate the value of the equilibrium constant. There isn't a mark here for giving the expression, which we gave in the previous question, so there was a mark for it already. But if you plug in the numbers, so the ammonia is squared, and then we're going to do the nitrogen, and the hydrogen will be cubed. And then there's a mark here for evaluating it and giving the answer. So 1 mark for the value of Kp, and the other mark is for the units. So plug all the numbers into the calculator and you'll get that it's 0.002988. And the units, if all the partial pressures are given to you in kPa, then you're going to have 2 lots of kPa on the top, 4 lots of kPa on the bottom, which means overall you've got 2 more on the bottom than on the top, so it's going to be kPa to the -2. So 2.4 is asking a bit of Le Chatelier's. It's asking, so if the enthalpy change is -92 kilojoules per mole, we know that's exothermic. It says state the effect, if any, of an increasing temperature. So if we increase the temperature, Kp will decrease because we are going to favour the backwards reaction. Okay, so our justification then, so the position of equilibrium is going to move to the left-hand side because it will favour the endothermic reaction, or it will move in the direction of endothermic change. You don't need to put this to get the marks in the answer, but obviously if you move more to the reactants, then the number is going to be smaller on the top, bigger on the bottom, so the value of Kp will decrease. And as we've covered many times in class, the only thing that actually affects the value of Kp is the temperature, so it will change with temperature, but it doesn't change with pressure or concentration or catalysts. So question 3 is about entropy and Gibbs free energy. 3.1 asks you to calculate the entropy change for the reaction. So if you remember, what we do is we take the sum of the entropies of the products and we take away from that the sum of the entropies of the reactants. So if we tot up so we've got 4 lots of nitrogen monoxide and 6 lots of water. So that's going to be 4 times 211 plus 6 times 189. And that's going to be our sum of our entropy of the products. Take away 4 lots of ammonia, so 4 lots of 193, and 5 lots of oxygen, 5 times 205. And then we take the reactants away from the products. And we get a final answer of plus 181. Now this is in joules per Kelvin per mole. So in part 2 of the question, we're asked to calculate the Gibbs free energy change using the entropy from the previous question. So you need to remember that delta G is equal to delta H minus T delta S. So they never give you that in the question. And then fill in the information they've given you. So delta H was minus 905. The temperature they've given you is 600 degrees C, so we need to convert that into Kelvin. So add 273, that's 873. And then you need to remember that the delta S needs to be in kilojoules, otherwise you can't take it away or add it to delta H, which is in kilojoules. So we just worked out on the previous page that delta S was 181, so we need to divide it by 1,000. So it's going to be 0.181 times the 873 taken away from the minus 905. So we get a final value of delta G is minus 1063 kilojoules per mole. So in 3.3, you're asked what would happen if the experiment was carried out at a higher temperature. How would this affect delta G? So you need to say that if the temperature was increased, then the amount you're timesing delta S by would increase. So you're actually going to be taking away a larger value from an already negative number. So it's actually going to end up giving you an even more negative value of delta G. So here we're being asked to describe the stages in how a heterogeneous catalyst works. So as always, when describing stages of the things that happen in several stages, I would break it up. I'd even number those stages. So I'd say step 1, that the reactants, and you can name them as ammonia and oxygen, or just say the reactants, are going to adsorb onto the surface of the platinum catalyst. In step 2, then the bonds that are within the reactants are going to weaken and eventually break, enabling new bonds to form. The reactant, or you can write that the reaction takes place. And then step 3, that the products then desorb and diffuse away from the surface of the catalyst. So in 3.5, we're asked for the oxidation state change in nitrogen from ammonia to nitrogen monoxide. So in ammonia, we can see it's got 3 hydrogens, which are always +1, so the N must be -3. And in nitrogen monoxide, it must be +2. We're then asked to give an equation for when ammonia reacts with oxygen, making nitrous oxide instead of NO. This is a case of get down what they've told you and see if you can work out what the other product is. So if we have ammonia and oxygen making the nitrous oxide, you can see we need to put a second ammonia molecule in to balance the nitrogens. And then if you look at what you've got left over, you're going to end up with 6 hydrogens and an oxygen. So if we make 3 molecules of water, we can then go back and say we're going to need a second oxygen molecule. So here we're asked for the full electron configuration of the calcium ion. So if we have a quick look at the periodic table, we see calcium group 2, it's got 20 electrons in total, so it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, and then it's 2 plus, so it would be 4s2 if it was just calcium, but because it's 2 plus, it would just be 3p6. So then we're asked to explain why the second ionisation energy of calcium is lower than the second energy of potassium. So if we're considering second ionisation energy, this is the energy to lose the second electron, not the first electron. So the easiest way to compare them is to say what it would be losing the electron from. So calcium would be losing its electron from the 4s, whereas potassium, which would be normally 3p6 4s1. If it's already lost 1, it would be 3p6. So to lose a second, it would be losing from the 3p. And as the 4s are further out from the nucleus than the 3p, and there is less shielding, then it's easier to lose an electron from the 4s, and therefore has a lower energy. So next we're asked to identify the S-block metal that has the highest first ionisation energy. Make sure you read the whole question, because I just read S-block first and went, oh, it must be helium, but it wants the metal, so it would be beryllium. The formula of the hydroxide in group 2, that's the least soluble in water, so you need to remember that the solubility of the hydroxides increases as you go down the group. Therefore, the least soluble would be magnesium hydroxide, and the mark is for remembering that the formula, because it's Mg2 plus, is going to have 2 lots of OH minus. So 4.5 is after an ionic equation and a little bit of a mole calculation. So it tells you how much barium chloride they've added to how much sodium sulfate, and asks you to give an ionic equation first of all, and then calculate which reagent's in excess. So first of all, we're making barium sulfate, so it's going to be the barium ion, which is Ba2+, plus a sulfate ion, SO42-, making barium sulfate. And remember, whenever you have an ionic equation for a precipitate, it's always aqueous plus aqueous makes solid. Okay, then we need to work out which reagent is in excess. So a quick little mole calculation for each of the reagents. So the barium chloride, we've got 6 centimetres, so 6 over 1,000 times 0.25, and that's 0.0015 moles. And the sodium sulfate, we need to do 8 centimetres cubed, so 8 over 1,000 times 0.15, and that works out as 0.0012. So it would seem that the reagent in excess is the one that we've got more of, so that would be the barium chloride. So to work out the total volume of the other reagent that needs to be used to make sure that we don't have anything left over, we need to make sure that we use the same number of moles of sodium sulfate as we use of the barium chloride. So if we take the moles of the barium chloride, 0.0015, and if we divide that by the concentration of the sodium sulfate, then we'll get the volume that we need to use, so 0.01 decimeters cubed, which is 10 centimeters cubed. So in 4.6, you're asked about different isotopes of strontium and asked to work out the percentage abundance of one of the isotopes. So why would they have identical chemical properties? Well, because they've all got the same number of protons and therefore the same number of electrons and therefore the same electron configuration, which is the thing that affects the chemical properties. So to work out the percentage abundance, you need to know that the relative atomic mass is 87.7, and it's told you that the 86 and 87 are in a 1-to-1 relationship. So if we say that the 87.7 is going to be, so 86 lots of X, we're going to call the abundance of 86 and 87 X. And we know that the 88 must have an abundance of 100 minus 2x. So minus the abundance of the other two. And if we then write this out as an algebraic expression and divide the whole lot by 100, so we're saying the total abundance is 100%. And then we end up multiplying the 87.7 by the 100. To get rid of the 100. So expand the brackets. Okay, and then if we group the numbers together on one side and the x's together on the other side, so we're going to end up with that 3x is equal to 30. So therefore x is 10. So if 86 has an abundance of 10, 87 has an abundance of 10, the 88 must have an abundance of 80. Final question then asks you to identify the ion with the longest time of flight out of these barium ions. So the one with the longest time of flight is going to be the one with the largest atomic mass, so barium 138. If it's been ionised by electron impact rather than electrospray ionisation, we know that it's just going to have a positive charge, but that its mass number will have stayed the same. So next we've got a time of flight calculation for the mass spectrometer, where we have to rearrange K equals half mv squared. So first job, if we're asked to calculate the length of the tube, we must need to work out the velocity. So if we rearrange to give us square root of 2ke over m is equal to v. And we know that m is got to be the mass of one particle in kilograms. So if 1 mole of barium 137 has a mass of 137 grams, one particle is 137 over 1,000 to get it into kilograms, and then over Avogadro's number to get one ion. And this should be a very, very small number. If you come out with a very large number, you know you've pressed something wrong in the calculator. So the mass of one particle must be very small. Okay, so then if we plug the numbers in to get the velocity, so we know we've got 2 lots of Ke. Ke was 3.65 times 10 to the minus 16. So 2 lots of that, divided by our value of m that we've worked out, so 2.2745 times 10 to the minus 25. And we're going to need to work out the square root of this. So we end up with a velocity of 5.66 times 10 to the 4. So quite a fast velocity for these particles. And then if we know that velocity is distance over time, and we're being asked to work out the distance, and we've been given the time, then we know that velocity times the time is equal to the distance. So if we do 5.66 times 10 to the 4 times the time taken, and we come out with a distance which is in metres and is usually 1.5 metres, between half a metre and 2 metres, so 1.54 metres is a reasonable distance. So question 5 is about acids and bases. First of all, you're asked for the meaning of the term strong acid, so that's one that's either fully dissociated or fully ionised when in solution. So next we're told about an experiment where hydrochloric acid and barium hydroxide, so that's a strong acid and a strong base, are mixed together, and you're asked to calculate the pH of the solution that forms at 30 degrees C. So you need to work out how many moles you have of the acid, how many moles you have of the barium hydroxide, work out which one is in excess, work out what the excess is, and then you can go on to work out the hydrogen ion concentration and the pH. So starting off then, we work out the moles of the hydrochloric acid, so that's the volume divided by 1,000 times the concentration. And then we need to do the same thing for the barium hydroxide, remembering barium hydroxide is BaOH2. So take the volume divided by 1,000 and times it by the concentration. So that's the moles of barium hydroxide. And because there are 2 moles of hydroxide ions per 1 mole of barium, we then need to go on to say that the hydroxide ion concentration is going to be that number of moles times 2. Well, the number of moles is going to be times 2. And then we can see which one is in excess. So after they react, then the hydroxide moles is going to be equal to, so the moles of hydroxide at the start take away the moles of the hydrochloric acid. And we'll see how many moles of hydroxide we have at the end of the reaction. Okay, once we've got the moles of the hydroxide ions, we then need it as a concentration. So you need to take into account how much volume there is there. So there was 10.35 centimetres cubed and 25 centimetres cubed. So we've got the number of moles divided by the total volume, which is going to be 35.35. And that obviously over 1,000. So we get a hydroxide ion concentration of 0.182. So if I move it up so I get a little bit more space, once we've got the concentration of the hydroxide ions, we know what Kw is at 30 degrees C. So we can rearrange it to get the hydrogen ion concentration. So H plus is going to be equal to Kw over the hydroxide ion concentration. And once we get the hydrogen ion concentration, we can plug it into our pH calculator. So negative log to base 10 of the hydrogen ion concentration will give us the pH. So the hydrogen ion concentration is 8.038 times 10 to the minus 14. So we know our pH is going to come out as between 13 and 14. So log to base 10 of 8.038 times 10 to the 14 is 10 to the minus 14. Remembering we need to do negative log to base 10. If we plug that into a calculator, comes out as 13.09, always giving pH to 2 decimal places. So we've seen 5.3 many times before. Why is it still neutral even though Kw has changed and the pH is different? And this is because the hydrogen ion concentration is still equal to the hydroxide ion concentration, so it's still neutral water. Next, asked to identify the oxide that could react to form a solution with pH 2. So you're looking for which one of these would give and which one of these is an acidic oxide. So if you look at the options, the aluminium one you need to remember is amphoteric. Sodium oxide, so metallic oxides are alkaline. Silicon dioxide doesn't react, it doesn't dissolve, so it wouldn't give a pH. So it's got to be the sulfur dioxide because non-metal oxides are acidic. So here we're asked for the Ka expression for an ethanoic acid. So normally you give H plus A minus over HA, but because they've told you they want it for a specific acid, you need to put in the CH3COOH in place of HA. So it's going to be H plus times CH3COO minus over CH3COOH. As always with equilibrium constants, it's products over reactants. Okay, next we've got a buffer calculation, so 5 marks, calculating the pH. So let's just quickly remind ourselves of what happens. So the equilibrium that's formed between a weak acid, so where HA turns into A minus and H plus. And if we think about the moles it's told us about, so we know we've got 0.025 moles of the salt. And the acid, we've got 0.035 moles. And that's worked out because we've got 500 centimetres cubed of 0.07 moles per decimetre cubed. So if we add 5 centimetres of 2 molar HCl, we're adding 0.01 moles. So we know all of that's going to get used up, and that will react with the A minus. So that's going to go down by 0.01 and turn into 0.015. And it's going to form more HA, so that's going to add 0.01. So that's going to go up to 0.045. Okay, or 0.045. So we now have our new number of moles for HA and A minus. We just need to turn them back into concentration. So the whole thing's happening in 500 centimetres cubed. So if you know the moles and you know the volume, you can work out the concentration. So 0.045 divided by 0.5 is going to be 0.09. And 0.015 divided by 0.5 is going to be 0.03. And then if we know that H plus is going to be equal to Kw times, and this is where we have acid over salt, so HA over A minus. So is going to be equal to 1.76 times 10 to the minus 5 times 0.09 over 0.03. So that's the same as 9 over 3, which is 3. So 1.76 times 10 to the minus 5 times 3 will be our new hydrogen ion concentration. And then to work out the pH, we use negative log to base 10. Come out with an answer of 4.277, so to 2 decimal places, that would be 4.28. So question 6 is about electrochemical cells, but it's slightly different to the questions we've seen before, because rather than having 2 different metal and solutions, we've got both sides are copper, but the reason there's a potential difference is because there is a difference in the concentrations used, which does mean that there's going to be a difference in the electrode potentials. So 6.1 asks how the salt bridge provides an electrical connection. So it allows the ions to move. It's really important that you say ions, that you don't talk about electrons moving, because the electrons move through the wire between the 2 copper electrodes. They do not move through the salt bridge. Okay, so it allows the ions to move. This completes the circuit. Okay, we're then told that the standard electrode potential for the Cu2 plus Cu electrode is plus 0.34. So that's the one that's got a 1 decimetre cubed solution. Okay, the 1 mole per decimetre cubed solution. So that would be the right-hand cell. Okay, but we then need to work out the left-hand electrode, and we know that the whole voltage, the whole cell is given a voltage of plus 0.16. So the EMF we know is plus 0.16, and that's going to be equal to the right-hand cell take away the left-hand cell. So if we work out then, so we know 0.16 is going to be our right hand cell. Okay, take away the left hand cell, which is the one we're working out. So if we rearrange the equation to give us that the left hand cell is going to be 0.34 minus 0.16. So we're going to end up with 0.18 volts. Okay, it says both electrodes contain a strip of copper metal. State why the left-hand electrode does not have an electrode potential of 0.34. Well, because it doesn't have 1 molar solution. So the standard electrode potential of 0.34 is only when we use a concentration of 1 mole per decimetre cubed. So 6.4 is interesting. You're being asked for the conventional representation. If you remember the acronym ROR, so ROOR, reduced, oxidised, oxidised, reduced. And this is interesting because both the left-hand and right-hand cells are the same system, even if they're not in standard states. So we've got copper solid turning into copper 2 plus aqueous on the left-hand cell. And then on the right-hand cell, we've got copper 2 plus aqueous turning into copper. And the arrows just show you to remind you how the species change and what the conventional representation shows. Okay. Right, you're then asked what would happen to the changing concentration of the copper 2 ions in the left-hand electrode. So if when it's allowed and over time it decreased to 0, so the concentration would increase. And eventually it goes to 0 because the concentration of the 2 cells would become equal. One would increase and the right-hand cell would decrease until they reached a point where both had the same concentration and there would no longer be a potential difference. So question 7 is about reactions of ions in aqueous solution, specifically aluminium ions. So we start off with aluminium chloride reacting with water, and a solution Y is formed that has a complex. So aluminium ions in a complex. So we would say that we get 6 water molecules and it becomes 3 plus 3 Cl minus. And then in part 2 we're asked to give an equation to show how complex ion Z, so the hexa AQA aluminium complex, can act as a Bronsted-Lowry acid with water. So if it's acting as an acid, it's acting as a proton donor. So when it reacts with water, it's going to donate protons to the water. So in doing so, it's going to lose some protons from the water molecules that are in the waters of the aluminium complex. I've run out of space a little bit here, but so plus H3O plus. So it's acted as an acid, it donated a proton. Then ask for 2 observations that you would make when it reacts with excess sodium carbonate. So if you remember, when aluminium hydroxide reacts with sodium carbonate, it acts as an acid, therefore it fizzes and gives off carbon dioxide, and you also get a white precipitate formed. Okay, and that white precipitate is because it continues to act as an acid with the carbonate until it forms the aluminium hydroxide water complex that has the right number of hydroxide ions within the complex to neutralize the complex so that it no longer has a charge and it becomes a precipitate. So we say the hexa aqua aluminium reacts with the carbonate and is going to form Okay, so an uncharged complex that will form the solid precipitate. So it's going to have 3 OH minuses. Okay. And no charge. And acid plus carbonate makes salt plus water plus carbon dioxide. And then we need to go back and balance it. So if it's lost 3 protons, we know it must make 3 waters and 3 lots of CO2. So it must have reacted with 3 lots of carbonate in the first place. Now, because aluminium compounds or aluminium complexes are amphoteric, the next part of the question is how it reacts with potassium hydroxide. So we can say, so a white precipitate would be formed. So we're still acting as an acid in this case because it's reacting with potassium hydroxide, which is a strong base. So it would swap 3, so the white precipitate would form when it forms the neutral complex with 3 waters and 3 hydroxide ions. Because it has no charge and therefore forms a precipitate. Okay, but if we then continue to add the hydroxide, I've written that equation in the wrong place. If we add further hydroxide, then the precipitate would dissolve because this neutral complex with the 3 hydroxides and the 3 waters is then able to react further with more hydroxide and become negatively charged. So you can just put with 1 hydroxide, you could put it with 2, but we'll start with 1. Okay, and forms a negatively charged complex. So question 8 is a 6-mark level of response question about structure and bonding. The key to these questions is working out, so you know there's going to be 3 things you have to do on the mark scheme, and it's about the detail you put into those 3 things. So it's using the question to work out what those 3 things are. So it tells us you need to use your knowledge of structure and bonding to explain why sodium bromide has a melting point that is higher than that of sodium and higher than that of sodium iodide. So from this, you know you've got sodium bromide and sodium iodide are both ionic. Sodium is metallic bonding, and then there's going to be something for the comparison. So I would break it up into, I'm going to explain what the bonding is in sodium and describe what goes on with metallic bonding. I'm then going to describe what goes on in ionic bonding and explain, so I can explain the bonding in the sodium iodide and the sodium bromide. And then I'm going to go on and explain compare them. And, even in fairly simple terms, just that this means that the bonding is stronger because the melting point is depending on the strength of the bond. And you can even go into explaining why there'd be a difference between the melting point of sodium iodide and sodium bromide in terms of the size of the relative size of the ions. Okay, I'm not going to talk you through the whole answer. I'll speed it up so that you get a faster version of my writing, but you can see how I've structured my answer and compare it to the mark scheme. 8.2 is a 6-mark calculation. There's going to be some mole calculation in here, but also there's a big clue that they give you the gas constant and a pressure in kilopascal, so you know you're going to have to rearrange PV equals nRT. So it asks you to calculate the volume in centimetres cubed when 250 milligrams of sodium are added to 500 centimetres cubed of water. So the first mark is for the equation, so remembering that sodium is going to react with water and it forms sodium hydroxide and hydrogen. And then going back and making sure it's balanced, we know that we're going to need 2 lots of sodium hydroxide and 2 lots of sodium and 2 lots of water to get the 1 mole of hydrogen. So if we know that PV equals nRT, we need to rearrange it so that volume is the subject. So if volume is going to be nRT over P. So first job is to work out the moles, what N. So work out N. So if we've got 250 milligrams, that's 0.25 grams. And if we divide that by the atomic mass of sodium, which is 23, we get that there are 0.01086 moles of sodium, okay, or 869. I've kept all the numbers from the calculator there. It's best not to round until you get to the very end. Looking at the equation, they react in a 2-to-1 ratio. So for every 2 moles of sodium, there's going to be 1 mole of hydrogen produced. So therefore, N is going to be half the value of the number of moles we've worked out previously. So if I half the 0.010869, I'm going to get 0.00543 moles, okay? So next step, if I know N, and I'm trying to work out V, R is given to us in the question, so we need to work out the temperature. So it says at 25 degrees C, so I work that out in Kelvin by adding 273, so that's 298 Kelvin. And the pressure is given to us in kilopascals. To put it into the PV equals nRT calculation, we need to transform that into pascals, so we need to times it by 1,000. So if we plug all the numbers into PV equals nRT, so the moles times the gas constant times the temperature in Kelvin, all divided by the pressure in pascals, so 101,000. Then we'll get a volume once we plug that into the calculator. So now this looks like a really small number, but this volume is in meters cubed. So we need to transfer from meters cubed into centimeters cubed, and the conversion factor is 1,000,000. So if we take our answer in meters cubed and times it by 1,000,000 or 10 to the 6, then we'll get an answer that is in centimeters cubed. So there you go, 133.3 centimetres cubed. Then it says to calculate the concentration in moles per decimetre cubed of the sodium ions in the solution produced. So concentration is moles divided by volume. You know how many moles of sodium you put in, so you know how many sodium ions there are in there. And you know the volume because you know it was added to 500 centimetres cubed of water. So 500 over 1,000 is 0.5. So we're going to do 0.01087 divided by 0.5 to get a final concentration of 0.0217 moles per decimetre cubed. So 8.4 is asking for a shape and a bond angle and a justification of the shape. So we're looking at the NH2 minus ion. So first job is to work out all the different electrons. So nitrogen's in group 5, it's got 5 outer shell electrons. It's then going to gain 2 electrons from each of the 2 hydrogens. There's a -1 charge, that's an extra electron. So there's 8 electrons in total. We know that there's only 2 bonding pairs because there's 2 hydrogens, so therefore the other 4 electrons must be involved in 2 lone pairs. So if we draw out the shape, so it's going to have 4 sets of electrons, but 2 of them are going to be bonding pairs. So there's the 2 hydrogens. And then the other 4 electrons are going to be 2 lone pairs. So here's the shape. Okay. What would we call that shape? So either V-shaped or bent. Yeah, put the negative charge on, put it in brackets. The bond angle, therefore, is 104.5 degrees, because at 4 sets of electrons would give you overall a bond angle of 109.5, but each lone pair reduces the bond angle by 2.5 degrees. So we take off 2 lots of 2.5, so take off 5 from 109.5 and you get 104.5. Justifying it, you need to say that there are 4 pairs of electrons around the central atom or around the central nitrogen, and they are going to repel each other and get as far apart as possible, which would give a bond angle of 109.5. You don't actually need to put that in your answer. And that lone pairs, so the lone pairs repel each other more than the bonding pairs repel each other, and a lone pair repels a bonding pair more than 2 bonding pairs. So lone pairs repel more than bonding pairs and therefore reduce the bond angle. So question 9 is everybody's favourite topic, electrochemistry. And in this one, it's where you're using electropotentials to predict what reactions will happen and what won't happen. So if we look, we're asked to identify the species that can reduce VO2 plus to VO2 plus. So we're looking for that equation at the top there to go in the forwards direction. So if we want that to go in the forwards direction, that needs to be the positive electrode. So we're looking for something that's more negative than it, or something that's lower value than it, that will be able to make that reaction happen. So if we look, the second equation with the VO2 plus to V3 plus, that's at plus 0.34. Okay, now if we look at our options for reducing agents, then the chlorine so chloride is too positive, so it's not going to work. But if we look, the Fe3 plus to Fe2 plus is less positive than the VO2 plus, so at the value of 0.77 is closer to the negative scale, so this would become the negative electrode and is able to reduce VO2 plus to VO2 plus without taking it all the way to being V3 plus. So it's really important that you pick something that's got a value in between the 2 vanadium equations, because you want it to reduce the first equation, but you want it to stay at VO2 plus and not reduce the VO2 plus into V3 plus. So it needs to have an electropotential that's in between 1 and 0.34. Therefore, you can use Fe3, you can use Fe2 plus because it's in between the 2, but the Cl minus is too positive and the zinc is too negative because it would do both. Okay, and the next part of the question, you're asked to give the oxidation state of the vanadium in the vanadium VOH2O5 2+. So what you need to do is look at, so the waters don't contribute, so the waters are all neutral, they don't contribute to the oxidation state. The oxygen in there does. The oxygen is -2, and overall the whole complex is coming out as +2. So the vanadium must be +4 to get past the -2 from the oxygen and take it all the way up to +2. So the answer is +4. So 9.3 continues with vanadium complexes, but it's just a standard transition metal question. So saying we've got this complex, it's got an isomer. So you should recognise that there you've got the cis complex because the 2 chlorines are next to each other. So we need to draw the trans version. So you need to draw the 2 chlorines opposite each other rather than next to each other. So I draw those on first and then fill in the water ligands. Okay. Now there's different names you can give for this type of isomerism. So you could call it cis-trans, you can call it EZ, because it is the same as EZ, or you could just say that they are stereoisomers of each other. Okay, all three accepted on the mark scheme. Okay, we're then told that heating ammonium vanadate produces vanadium oxide, water and one other product. So this is one of those questions where you need to write down the formulae of the things you've been given and try and work out what the other product is. So if we write out the ammonium vanadate, vanadium oxide plus water, and then we can have a look, try and balance it a little bit and see what must be there. So at this point I can see I must need to use 2 lots of ammonium vanadate because I need to get V2 in the V2O5. That's going to give me 6 oxygens on that side, and I've got 6 oxygens in the products. There's 2 hydrogens in the products, and I'm going to have 8 hydrogens total, but I'm also going to have 2 more nitrogens. So I think the other product is going to be ammonia, so NH3. Looking at what's there. And to get the right number of hydrogens, we're going to need 2 lots of ammonia. So continuing on to question 9.5, we're asked about vanadium oxide being used as the catalyst in the manufacture of sulfur trioxide. This is from the contact process. So you need to know that this process is turning sulfur dioxide into sulfur trioxide, so SO2 into SO3, and that V2O5 is the catalyst. And in that process, the V2O5 gets converted into V2O4, and then the catalyst gets regenerated by reacting with half an oxygen. So overall, the reaction is that the SO2 reacts with half an oxygen and turns into SO3, but it goes via the vanadium oxide catalyst, which gets regenerated because it offers a lower activation energy. But these are the 2 equations you need to remember for that reaction. So the final question on this paper 1 is a 7-mark calculation amount of substance question, which covers a titration, but where you're working out the number of moles of water of crystallization. With all of these questions, I would suggest you look for something you know the most about, and I would normally say you start with the titration, get the data and the number of moles from the titration, and then put those back into the initial reaction. So if we look, we've been given plenty of information about the sodium hydroxide. We've been given its volume and its concentration. So first job, stick with what you know. You can work out the moles quite easily. So the moles of sodium hydroxide used in the titration is going to be 26.6 over 1,000 times the 0.15. So that will give us a number of moles of 0.00399. Okay. Now, we therefore know that the moles of hydrochloric acid used, because they react 1 to 1, you don't need to write the equation here, but you could mentally jot it down on the scrap paper. So they react 1 to 1, so we know that in 25 centimetres cubed of HCl, there's the same number of moles as there were in the NaOH. Now we know that those 25 centimetre portions were taken out of a 250 centimetre cubed flask. So the moles of HCl that were in the flask, so in the volumetric flask, must be 10 times the amount that's in the 25. So it's going to be 0.0399. Okay. So that's all the information we can get from the titration. So the second part of the question is to look at the reaction, because we're trying to find out about sodium carbonate using the information from the hydrochloric acid. So if we go back to the reaction and we go, right, so we know how much hydrochloric acid we started off with. So our initial moles of hydrochloric acid. And that is, so we had 200 centimetres cubed of 0.25 molar in a beaker. So 200 over 1,000, 0.2 times 0.25 is going to give us how many moles of hydrochloric acid we had at the start. So 0.050. And then I need to work out how many moles are left after the reaction. So I know how many were left because they went through to the titration. I need to work out how many moles of hydrochloric acid actually reacted. So if I do the initial moles, take away the moles that were in the flask, so the moles that we did the titration with, then I can work out how many moles must have reacted with the sodium carbonate. 0.010 moles reacted with the sodium carbonate. And then quickly jot down the reaction equation for the reaction that happened that it tells you about at the very start. So the sodium carbonate reacts with hydrochloric acid and forms sodium chloride and carbon dioxide and water. And they react in a ratio of, if we just check the equation, we're going to need to use 2 lots of HCl and get 2 lots of NaCl. So they react in a 1:2 ratio. So if I know how many moles of HCl reacted, then I must know that the number of moles of sodium carbonate will be half the number of moles of hydrochloric acid. Okay, so we've been told how many grams of the hydrated sodium carbonate we put in, 627 milligrams. So we then need to say, if we know the 627 milligrams, that's 0.627 grams. If I know the mass and I know the number of moles, I can work out an MR. So if we do mass divided by moles, we'll get the MR of the hydrated sodium carbonate. So 0.627 over the number of moles, 0.00505. And we get an MR of 124.16. Now we know that this 124.16 is coming from Na2CO3 X H2O. So we know that one chunk of it is coming from Na2CO3, and the MR of that is going to be 2 lots of 23 plus 12 plus 3 lots of 16, which is 48. So that all adds up to 106. So of the 124.16, I know 106 of it is down to sodium carbonate. So whatever is left over is down to water. So the difference between them is approximately 18, which is one mole of water. Okay, so so when you look at the formula Na2CO3 X H2O, we know that X must be 1. And that is the end of June 18 question paper 1.